There we go. So today we're going to talk about the inversion of the Laplace transform. But before we focus on the inversion of the Laplace transform, knowing that a few students still struggle with linearization, see, it's always important to know the reason why you're doing something. Because we started with a chapter on process control overview, and then there was process modeling principles. And from the process modeling principles, we had different models. And these models, they were differential equations, which we couldn't solve. We just described the models and then we stopped there. They were differential equations, all right? And then I said to solve these differential equations, we needed Laplace. All right. And Laplace transforms can only be applied to linear systems. Can only be applied to linear systems. So from the differential equations obtained as a result of process modeling, we have different differential equations, all right? But these equations are not necessarily linear. And I also mentioned that the theory of process control is almost exclusively based on linear systems. So if you happen to have a non-linear system, so it is important for you to linearize your system before you could use Laplace transforms. Laplace transforms only applies to linear systems. So you get your models, you linearize your models, then you can apply the Laplace transform to solve the differential equations, which are the models that we obtained from mathematical modeling principles. So in a nutshell, this is what we've covered today. Each other very, very nicely. So we describe the models from the mathematical modeling principles. Then we check if there's a need to linearize. Remember that I'm not saying that all systems are non-linear. Some of them are linear. Those that are linear, you can solve them by Laplace transforming them straight away. However, when you're dealing with non-linear systems, it is important for you to linearize them because you can't Laplace transform a non-linear system. That's very important for you to note. I could give you a question where the models are non-linear, all right? Do not be quick to Laplace transform those systems. It's important to linearize before you could Laplace transform any systems that you're dealing with. So we talked about Laplace transforms, and we were able to, given a differential equation, we're able to Laplace transform it and get the result in S domain. Laplace transform it, you obtain the S domain, all right, which is the Laplace domain. But our aim is to have our solution in the T domain, all right, time-wise. So to go from the S domain or the Laplace domain to the T domain, what we need to do is to inverse the Laplace domain expression. That's why it's important to use the inversion of Laplace transform so that we could go from the S domain to the T domain. All right, so let's now dive in. Inversion of the Laplace transform. I'm going to repeat myself again. So in order to invert Laplace transforms, what we're going to do in this course is going to use the method developed by the mathematician called Heaviside. So method, the Heaviside method. So we're going to use the Heaviside method to invert Laplace transforms. So this method or this approach is also called the partial fraction expansion. So I will use partial fraction expansion more often than Heaviside. So to invert the Laplace transforms, you're going to use the partial fraction expansion. I'm sure it rings a bell. You have used it somehow, somewhere in the past. So let's assume that the Laplace transform of an unknown function is defined by, right? So assume that the Laplace transform of an unknown function y of t is given by q of s over p of s, where both q and s and p of s are polynomials. So in addition, so these are polynomials of different orders. We could say qs is of order n, s, and this is of order n. For example, in addition, ps is called the characteristic equation. So we've defined our function, which is in the S domain, which is a ratio of two polynomials, such that one is of order S and the other of order N. So how do we apply the inversion of Laplace, right, to this function? 3 steps are recommended. So I'm going to list the 3 steps that one has to follow. Given a function in the S domain, how do you invert it to, how do you convert it to the T domain? All right, so 3 steps are necessary. The first step is you need to expand the ratio Q of S over P of S into series of fractions. So these are the 3 steps, all right? I'm not writing everything down because I know I'm being recorded. So when you watch the video, you'll be able to find your way out easily. So first step, expand QS over PS into a series of fractions. And how do you do that? So you have y of s will be equal to q of s over p of S, this will be equal to C1 over R1 of S plus C2 over R2 of S plus C sub n over R sub n of S, where C1, C2, and Cn are constants, right? Where C1, C2, and Cn are constant, and R sub 1s, R sub 2s, R sub ns, these are low order polynomials. So by low order polynomials, that means you can have a first order, second order, and so on. So first step, you expand the ratio of two polynomials into a series of fractions. Second step, you need to compute the values of C1, C2, right? In other words, compute the values of the constants or determine the values of the constants. So we're going to determine these constants using the previous expansion, right? You expand and then you'd compute Cn and C2 up to Cn using the expansion in step 1. Step 2. Or step 3 now. Find the inverse Laplace transform. Which is denoted by L power of -1 of every partial fraction. So you do it as follows. So in other words, when you invert Laplace transform, you're going to go from the S domain to the T domain. So initially, the Laplace transform in S domain was capital Y of S. So after the inversion, you're going to have small y of T, which will be equal to the inverse Laplace of the series of fractions. So it'll be C1 over R1 S plus the inverse Laplace of C2 over R2 sub S plus it continues inverse Laplace of Cn over R sub n of S. So this is how you invert Laplace a given function in the S domain. But it's very important to note that when given a ratio of two functions, such as this case, you have Q of S over P of S. All right, it's important to note that this ratio is governed by the characteristic equation. In other words, it is governed by the form of PS and the roots of PS. So when you are given a ratio of two polynomials, right? Note that its expansion into series of fractions is governed by its denominator, which is the characteristic equation. And here we need to look at its form and its roots. Very important. So when we look at the roots, we've got two most likely scenarios. So the polynomial P of S could have n distinct roots, by that I mean real or complex roots. And number two, the polynomial could have multiple roots. So we're going to look at the most likely case that our characteristic equation is likely to exhibit. So two cases are distinguished. The first one is that PS has n distinct roots. This means this root could be real or complex. Second case, P of S has multiple roots. So let's look at these two cases. First one, distinct real roots of PS. So for this, we're going to consider the Laplace transform of a given function, all right? Consider the Laplace transform of the function y of t given by y of s squared minus s minus 6 over s cubed minus 2s squared minus s plus 2. As you can see, the numerator is a polynomial in S, which could be called QS, and the denominator is a polynomial in S, and we call it PS, our characteristic equation. Remember, what we want is we're considering one case where the characteristic equation has got distinct real roots, but we need to show you how we can apply the inversion of Laplace to this function. So the first step here is we need to expand our ratio into a series of fractions. So to do that, we need to find, or we need to factorize the denominator. And one of the ways to factorize is by finding the root of PS, which is s cubed minus 2s squared minus s plus 2. We have a polynomial of order 3, and we need to find its roots. I hope you still remember. Otherwise, this will be a homework. So if you do your calculation, the following are the roots of this polynomial of order 3. Because we refer to this polynomial as P of S, so I'm going to call the roots as P1, P2, and P3. As a hint, you can use the Hana method to solve this equation. So you've got the first root is positive 1, second one is negative 1, and third one is positive 2. So these are the roots of this characteristic equation. In other words, we can rewrite PS as s minus 1 into s plus 1 into s minus 2. So we can now substitute these factors into the given function. Y of s will be equal to s squared minus s minus 6 over s minus 1, s plus 1 into s minus 2. Now we're going to apply step 1 in full. We're going to expand into partial fraction. So we're going to have capital YS will be equal to C1 over S minus 1 plus C2 over S plus 1 plus C3 over S minus 2. We know that once we've got this, we need to compute the constant. So if we skip that step for now and then go to step 2 and find the inverse Laplace transform of this function. So what we're going to do is we apply Laplace on both sides of this function. So we're going to have Laplace going to inverse Laplace transform this function. It's going to be inverse Laplace transform of capital YS. This will be equal to the inverse Laplace of each partial fraction plus the inverse Laplace of C2 over S plus 1 plus the inverse Laplace transform of C3 over S minus 2. We know the inverse Laplace transform of YS is YT. So to go from S domain to the T domain, you inverse Laplace transform the given function. And this will be equal to apply the properties. So the properties of Laplace transforms. So the C1, which is a constant, can be taken out of the inverse Laplace transform. So going to remain with the inverse Laplace transform of 1 over S minus 1. If you've got your tables, you would see that the inverse Laplace transform, I'm going to find my table. I don't know if you'll be able to find yours. So we know that, let me find my table. We know that so I'm going to open the bracket before I could continue. We're going to erase this, all right, and then come back to it. We know that if f of t is equal to e to the power of at, its Laplace transform, taking this from the condensed table of Laplace transforms, this is 1 over s minus a. So this means the Laplace transform of f of t is equal to 1 over s minus a. But now we're interested in performing the inverse Laplace transform. So the inverse, we're going from the right hand side to the left hand side. Hence we say inverse Laplace transform. In other words, the inverse will be denoted as 1 over s minus a will be equal to e to the power of at. So from the condensed table of Laplace transforms can go from one side to the other and vice versa. And if you look at what we have in our partial fraction expansions, we have 1 over s minus 1. In other words, our a here is 1. Hence, the inverse Laplace transform of 1 over s minus 1 will be equal to e to the power of t because our a is 1. So we also have another partial fraction, which is c2 over s plus 1. So we can still focus on this table, where we know that the inverse Laplace transform of 1 over s minus a is e to the power of at. But now we want to find the inverse Laplace transform of 1 over s plus 1. I am neglecting the constant because it's been removed as per the properties of Laplace transforms, all right? So here, this quantity can be rewritten as the inverse Laplace transform of 1 over s minus 1, so that we keep the negative sign here. In this manner, then the inverse will be equal to e. Remember that now our a is negative 1, to be e to the power of negative 1 times t. I hope everybody is with me. I can't see when you raise your hands, so my advice to you is whenever you feel like you need clarification, you're welcome to speak up. I will pause and see if I can help you. So the next partial fraction is c3 over s plus 2. So the inverse Laplace transform of this function, again, just going to remove the constant and then put 1 over here. This is the same as the inverse Laplace transform of 1 over s minus 2, so that our a is no longer 1 but negative 2. Hence, the inverse Laplace transform of this function becomes e to the power of minus 2t. So considering all this, I'm going back to my note now. We can say that the computer is giving me problem now. Okay, there we go. So we can say that we have, I'm going to write y of t, which is equal to inverse Laplace transform of c1 over s minus 1 plus inverse Laplace transform of c2 over s plus 1 plus inverse Laplace transform of c3 over s plus 2. I have performed all these inverse Laplace transforms. I'm just going to sub. So y of t will be equal to, remember the c1 will come out, we're going to end up with c1 e to the power of t plus c2 e to the power of negative t plus c3 e to the power of, did we say 2t? Be careful, we have s plus 2. Let's go back and double check. According to our table, we've got 1 over s minus a, which is equal to e to the power of 8at, all right? The inverse will be e to the power of 8t. And then we said when you have s minus 1, you're going to end up with e to the power of t, which is correct. When you have 1 over s plus 1, you have minus minus, this will be negative t. But we made a mistake. We do not have 1 over s plus 2, but we have 1 over s minus 2. But it's always good to know when you have plus, this is how you're going to operate. But when you have the inverse Laplace transform of 1 over s, this is negative 2, this is plus, and this will work fine for that. But when you have 1 over s minus 2, this will be equal to e to the power of negative 2, negative 2t, because our a is 2. Remember, initially we had 1 over s minus a, and here we have 1 over s minus 2. So our a is 2. We sub 2 in the expression, in the original expression. Hence, the inverse Laplace transform of 1 over s minus 2 is e to the power of 2t. However, when you have 1 over s plus 2, then you're going to end up with e to the power of negative 2t. Please do not be confused. So then we have our function in the t domain. But for the system to be fully described, it's very important to find the constant. So now I'm going to show you how to find the constant. I'm going slowly, the first part, because it's very important that you understand. But as we proceed, I will speed up a little bit. How do we find the constants? Compute C1 or compute constants. We start with C1. How do you find C1? So what you're going to do is you're going to multiply the y over s function by s minus 1, y s minus 1, because it is the denominator of C1, s minus 1, and then set s minus 1 equals to 0 so that s will be equal to 1. So you multiply y of s by c minus 1. After the multiplication, ensure to cancel any terms that can be cancelled. Thereafter, substitute s by 1. Do not do both at the same time. You're going to get yourself into trouble. So which ys to use? I'm going to show you. We know that it's been given to us as ys is equal to s squared minus s minus 6 over s squared minus 2s squared minus s plus 2. This is what was given to us, but going to use the expression after factorizing the denominator. So we know that this is also equal to s squared minus s minus 6 over s minus 1 into s plus 1 into s minus 2. So when I say multiply ys, I mean use the second version of ys. Right, so I'm going to rewrite it. It's going to have s squared minus s minus 6 over s minus 1, s plus 1, s minus 2. I said you're going to multiply ys, or I would say you're going to multiply, I can just say ys by s minus 1. So we know that this is equal to C1, the expansion version, over s minus 1 plus C2 over s plus 1 plus C3 over s minus 2. So we're going to multiply both sides of this expression by s minus 1. So the whole thing here will be multiplied by s minus 1, and the whole thing will be multiplied by s minus 1. All right. So here we can cancel anything that can be cancelled, and then we can distribute s minus 1 inside the bracket. So we're going to continue. Remember, I told you before you could substitute s into the expression, ensure that everything that needs to be cancelled has been done. So we're going to remain with s squared minus s minus 6 over s plus 1 into s minus 2. This will be equal to, I'm going to distribute s minus 1. I have c1 times s minus 1 over s minus 1 plus c2 times s minus 1 over s plus 1 plus c3 s minus 1 over s minus 2. Check, as you can see, this can go with that one. There's nothing else that we can cancel. I'm going to write this as s squared minus s minus 6 over s plus 1 into s minus 2 to be equal to c1 plus c2 into s minus 1 over s plus 1 plus c3 s minus 1 over s minus 2. Now that we've cancelled everything that needed to be cancelled, we can then set, let s be equal to 1. Remember that you find this value by equating the denominator of s1 of c1 to 0 and solve for s. Let's sub s equals 1. So now we're going to sub. We're going to have 1 squared minus 1 minus 6 over 1 plus 1 into 1 minus 2 equal to c1 plus c2 1 minus 1 over s plus 1 plus C3 1 minus 1 over S minus 2. This will give us 0, hence this term. No, let's sub here as well. 1 and 1. And 0 over any number, it's 0. So this will also be equal to 0. We remain with 1 minus 1 minus 6. So this gives us, we have, please, it's 1 minus 1 minus 6. What do you think the answer is? And a student, they always, because once you get this wrong, and then everything else becomes incorrect. I want somebody to tell me what is the answer in the denominator. So this will be 0, so it will be negative 6 over 2 times negative 1. This will be negative 2 equal to C1. That means our C1 is equal to 3. So we're going to obtain C2 in the same manner. So I'll do C2 bit by bit, C3 bit by bit, and then we'll speed up. Compute C2. So what we do is, remember, the denominator and the C2 is S plus 1. So what we're going to do is multiply YS by S plus 1, and then set S plus 1 equals 0 such that S is equal to negative 1. I'm saying such that, but I'm putting an incorrect symbol. So let me just try to erase. My pen sometimes refuses to erase. Okay, now leave it as is. So there we go. I think it will do it now. Troop doesn't want to. So I'll move on. So now we need to compute C2. Again, we have S squared minus S minus 6 over S minus 1, S plus 1, S minus 2. We multiplied by S plus 1, which is equal to C1 over S minus 1 plus C2 over S plus 1 plus C3 over S minus 2, and we multiply everything by S plus 1 so that we do not change our expression. After doing so, we check for any like terms and then cancel them off, and then distribute S plus 1 on the other side. So we have now S squared minus S minus 6 over S minus 1 into S minus 2. Do not try to expand, just leave it as is. You're gonna waste your time. Distribute, we're gonna have C1 into S plus 1 over S minus 1 plus C2 into S plus 1 over S plus 1 plus C3 into S plus 1 over S minus 2. Let's cancel again. Let's look for like terms and then cancel them off. Let me put the 2 back here. This pen, okay, there we go. So that's term, with that we go. That's it. So we can rewrite this as S squared minus S minus 6 over S minus 1 into S minus 2 equals to C1 into S plus 1 over S minus 1 plus C2 plus C3 S plus 1 over S minus 2. Nothing to be cancelled. We can now substitute. Let's substitute S equals negative 1. Let's do that. So we're going to have -1 squared minus -1 minus 6 over -1, -1 minus 2 equals to C1, -1, 1 over S, not S, but -1 minus 1 plus C2 equals to C3, not equal, but plus C3, -1 plus 1 over, this is C3, -1 minus 2. Let's do the math. We're going to have 1 plus 1 minus 6, that is -4, over -2 times -3, that is 6. That is 6 because -2, -2, yes, times -3, that is 6, equals to -1 plus 1, this term will be equal to 0. Any number 0 divided by any number is 0, so remain with C2. Then conclude and say C2 is equal to -2 over 3. Let's move to C3. So my -2 over 3 has shifted. So this is equal to -2 over 3. Compute C3. So you do the same. Compute. You multiply YS. This time around, the denominator C3 is S minus 2. So multiply YS by S minus 2, and then set S equals 2. Similarly, we're going to have S squared minus S minus 6 over S minus 1, S plus 1, S minus 2 times S minus 2 equals to C1 over S minus 1 plus C2 over S plus 1 plus C3 over S minus 2 times S minus 2. Cancel common terms. Got these two like terms, they've gone out. Then with S squared minus S minus 6 over S minus 1 into S plus 1. This is equal to, we distribute S minus 2. We're going to have C1 times S minus 2 over S minus 1 plus C2 over S plus 1 times S minus 2 plus C3. When you distribute, the S minus 2 will cancel off. This has shifted. I need to fix it. This S minus 1. S equals 2, to be 2. We're going to have 2. Wonder why some of my stuff are being left behind. 2 squared minus 2 minus 6 over 2 minus 1, 2 plus 1 equals to C1, 2 minus 2 over s minus 1 plus c2 2 minus 2 over not s but 2, and then 2 plus 1 plus c3. You do that, 2 minus 2 is 0, 0 over any number, return 0. This will be 0. And then we're going to have 4 minus 2, that's 2 minus 6, that's minus 4. Minus 4 over 2 minus 1, 1 times 3, that's 3. This will be equal to C3. We've computed all the constants. We can now substitute. Okay, so that's what we have. And we go down. So y of t after substitution will be equal to, the first c1 is 3 times e to the power of t plus p minus, not plus because minus 2 over 3, minus 2 over 3 e to the power of negative t, and negative 4 over 3 e to the power of 2t. So this is our solution in the t domain. So we're going to look at another case, distinct complex roots. We did distinct real roots of p of s. Now we're going to look at the other case of distinct complex root of our characteristic equation, and then show you how you're going to obtain the constants, or how you're going to first Laplace transform a given function in the S domain. So second, we'll look at distinct complex roots of P of S, our characteristic equation. So let's consider the following Laplace transform. Y of S equals to S plus 1 over S squared minus 2S. So this is the problem. My S and my 5s, they look alike. I'll do my best to make them look different. This is my 5. Everything else is S. So S plus 1 over S squared minus 2S plus 5. Remember, the first thing, we need to find the roots of our characteristic equation. So you've got Q. Oops. I wonder what's going on with my screen. It keeps on shifting. Okay, so this is equal to Q of S over P of S. We need to find the roots of P of S, right? So if you look at it, the discriminant of this equation is a -1. And when you solve it, remember that in complex numbers, j squared or I squared in other books is equal to -1. So j squared -1 I squared is equal to -1, complex numbers. Hope you still remember. So you're going to solve this, all right? And you would find the root, because our characteristic equation is P of S. So the first root, P1, is equal to 1 plus 2j, and P2 is equal to 1 minus 2j. So if you still have issues finding roots, please, there are plenty of videos on YouTube that could help you refresh your memory. I don't want to go through that, it's going to take me time. So So we've got, as you can see, these two roots are what we call in complex numbers, complex conjugates, right? Because the imaginary terms only differs by the negative, by the sign, so plus and minus. These are complex conjugates. So we can write PS, which is s squared initially minus 2s plus 5. We can say this is equal to s minus 1 plus 2g, just factorizing, and s minus 1 minus 2g. So we can then substitute this and then say y of s is equal to s plus 1 over 1 plus 2j into s minus 1 minus 2j. Now we can use the 3 steps. Expand into a series of fractions. Step 1, expand or expansions into a series of fractions. Then we can say y of s is equal C1 over, you can use any constant, you can use A, B, whatever that you feel comfortable with. C1 over S minus 1 plus 2J plus C2 over S minus 1 minus 2J. Again, if we skip step 2 and apply the inverse Laplace transform, so we're going to have inverse Laplace transform of Ys equals to the inverse Laplace transform of C1 over S minus 1 plus 2J plus the inverse Laplace transform of C2 over S minus 1 minus 2J. All right, so we know that the inverse Laplace transform of capital Ys is small yt. This will be equal to, we can take out the constant, and considering, again, I think I need to open another bracket just to refresh your memory. So you have your f of t and your f of s. So when you have e to the power of at, then its Laplace transform is 1 over s minus a. But in look at what we have. Our a is 1 plus 2j. That means the Laplace transform of this function will be e to the power of 1 plus 2j times t. Are you with me? Because our a is 1 plus 2j. And the Laplace, don't forget the constant C1 plus here again, but here we have negative 1 minus 2j. So C to the constant, then the inverse Laplace transform of this function will be e to the power of 1 minus 2j times t, because our a is 1 minus 2j. So let me write it neatly. Then we can say y t is equal to c1 over e to the power of 1 plus 2j into t plus c2 e to the power of 1 minus 2j into t. We've solved that system. So now we need to find the constant. I thought we were done. We need to find the constant to fully describe the system. We're going to use the same approach, but it will be a little different this time around. Let's compute C1. All right, everybody knows what we do. We're going to multiply both sides of ys by, because we want to find C1, and we know that in the expression of ys, C1 is below the denominator below C1 is, it is s minus into 1 plus 2j. So we're going to multiply much smarter to say both sides of ys by this will be s minus square bracket 1 plus 2j and then set s to be 1 plus 2j. Same approach. I keep on leaving some stuff behind, which is not good, and it takes time to erase. Okay, there we go. So we have s equals to 1 plus 2j. So what we do now is we've got s plus 1 over s minus 1 plus 2j into s minus 1 minus 2j. So we're going to multiply this by s minus 1 plus 2j, and this will be equal to, I'll need space, so I'm just going to put equal to C1 over s minus 1 plus 2j plus C2 over s minus 1 minus 2j times s minus 1 plus 2j. Right, let's cancel all the common terms. So this will go with that. And then we're going to distribute. So we're going to remain with s plus 1 over s minus 1 minus 2j. And this will be equal to, after distributing, this will fall with that. We're going to end up with C1 into s minus 1 plus 2j. C2, it's C1, not C2, over s minus 1 plus 2j. Now it's this that is going to cancel with that, not the other way around. Just going ahead of myself. So that means going to remain with C1 plus C2 into, why is it disappearing? C1 minus C2 into s minus 1 plus 2j over s minus 1 minus 2j. So there's nothing else that we can cancel. Substitute s by 1 plus 2j. So we're going to have 1 plus 2j plus 1 over 1 plus 2j minus 1 plus 2j. And this will be equal to C1. Why? Because when you sub 1 plus 2j here, you're going to end up with 1 plus 2j minus 1 plus 2j. So this term will be equal to 0. So C2 will disappear. I'm just, skipping some steps because I know that you are. We continue with C1, which is equal now to 2 plus 2j. Remember, j is our imaginary number, all right? And then we end up, the 1 will disappear, we have 4j. Remember that in complex numbers, you do not leave the imaginary number at the bottom, you need to conjugate. So if you do that, so before we do that, we can cancel. We can factorize and then cancel. So we're going to end up with 1 plus j over 2j. We're going to conjugate times 2j over 2j. Oops, being left behind. So we want to remove the imaginary term at the bottom. So we times the numerator by 2j and the denominator by 2j. Remembering that j squared is equal to -1. So we can say C1 is equal to (2j into 1 plus j) over 4j squared. This is equal to 2j plus 2j squared over 4j squared. Substituting j squared, -1. So you're going to end up with 2j plus 2 into -1 over 4 into -1. And this will be equal to -2 plus 2j over -4. You can simplify further so that C1 becomes 1 minus j over 2. All right, you can just take the -2 out. Remain with 1 minus j over -4. Cancel, remain with 1 over 1 minus j over 2. So this is, at least everybody has seen how to compute the constants when dealing with complex roots. So compute C2, similar approach. Please do it at home. All right, so C2 is equal to 1 plus j over 2. Once you have the constant, you can substitute them in the expression of y of t, which is 1 minus j over 2 e to the power of 1 plus 2j of t plus 1 plus j over 2 e to the power of minus 2j of t. Please find this at home, because in an assessment, a test, or an exam, I would want to see all these steps. Practice at home. Last one, we're going to look at multiple roots. So we've looked at distinct real roots, distinct complex roots. Now we're going to look at multiple roots of our characteristic equation. Next one and last for the day. Multiple roots of P of S, which is our characteristic equation. So let's consider the following Laplace transform. Where S that is equal to 1 over S plus 1 cubed into S plus 2. So here our characteristic equation has been factorized, so no need to find the root. Very easy to find the root, all right? S plus 2. So the roots of PS will be, I wonder why it's being shifted all the time. P plus 2 so the roots of PS are just equate each factor to 0, and then you have 1. It's negative 1, so P, you can say P1, P2, and P3. The order is 3. We're going to have 3 roots, negative 1, and P4, that is equal to negative 2. So now the next step, again, negative 2. So first step, expand or expansion into partial fraction. So what we do is y of s will be equal to, which is equal to 1 over s plus 1 cubed into s plus 2 equal to C1. I think I need space. Let me just rewrite this, keeping in mind that I will need space. So ys is equal to 1 over s plus 1 cubed s plus 2 is equal to into partial fraction C1 over s plus 1 plus C2 over s plus 1 squared plus C3 over s plus 1 cubed. So when you have multiple roots, all right, plus C4 over s plus 2. So this is how you expand this function into partial fractions. Again, we're going to skip step 2, which consists of finding the constant or computing the constant. We're going to use the inverse Laplace transform and then compute the constant at the end. So step 3, inverse Laplace of y of s should be equal to the inverse Laplace of C1 over s plus 1 plus inverse Laplace of C2 over s plus 1 squared plus the inverse Laplace C3 over S plus 1 cubed, and plus the inverse Laplace transform of C4 over S plus 2. All right. So here, I'll give you another condensed table with these functions. As I told you, for any assessment, I will give you condensed tables of functions of interest so that you don't have to struggle or derive them yourself. So the inverse Laplace transform of this function is y of t. This is equal to, and the inverse Laplace of the first term be c1 e to the power of negative t. We've got plus now. Initially we had negative sign, and plus this one, it's not in your notes yet, but I'll send you a condensed table. This will give you c2 e to the power of c2t e to the power of negative t plus c3 over 2 t squared e to the power of negative t plus c4 e to the power of negative 2t. Right? I can always come back to this if you, when you receive the condensed table and you still struggle, you can still always come back to this and then bring clarity. So once we have inverse Laplace transformed all these functions, so the next step is we need to compute the constant. C1, C2, C3, and C4. So this one, we need to look at the function that we have. We can compute C1 and C4 easily because it's similar to what we've just done. So we're going to start with the easier constant to get and then finish with the more challenging ones. Because if we focus on computing C1, compute C1, so what we're going to do, we're going to multiply both sides of ys by, this will be s plus 1. We're going to multiply by s plus 1. Or let's start with C4. Let's compute C4, then go to C1 is likely to give us a problem. Let's compute C4. So C4, what we're going to do is going to multiply ys by s plus 2. All right, multiply both sides of ys by s plus 2, and then set s equal to negative 2. Same approach as previously. So here we're going to have one over s plus 1 cubed into s plus 2 times s plus 2, which be equal to C1. I'll distribute straight away. So if we distribute, you're going to have C1 over s plus 1 into s plus 2 plus C2 into s plus 2 over s plus 1 squared plus C3 into s plus 2 over s plus 1 cubed plus c4 s plus 2 over s plus 2. Cancel all the common terms. So cancel those two. Here going to remain with 1 over s plus 1 cubed. Oh, I'll just skip a few steps again because everybody should now understand. After cancelling all the like terms, next step is to sub s equals -2. If we do that, we're going to end up with 1 over -2 plus 1 to the power of 3 equals 2. If you sub -2 here, this will be equal to 0. -2, this will be equal to 0. -2, this will be equal to 0. Going to remain with C4. This means C4 is equal to -2 plus 1 is -1 to the power of 3. That's -1. So C4 is equal to -1. So we have determined C4. So we need to find C3, C2, and C1. So my time is up. So on Friday, we're going to continue finding the rest of the constants. And then I will introduce initial and final value theorem. It's very like in 15 minutes, we should be able to finish. And in the meantime, I'll send you tutorials on Laplace transform so that we will do the tutorials after the 20 minutes or 15 minutes of lecture on Friday. You're gonna go through the third question. Please make sure that you attempt the third questions so that by Friday, you're gonna finish them and Monday we start transfer functions. Any questions? So no question. I'm going to stop the recording. Stop.